All right, hi everyone. Welcome back to CS330. And today we'll be talking about hierarchical reinforcement learning and skill discovery. Let's see if this works. All right, so the plan for the lecture is as following. First, we'll discuss why we should work on things such as hierarchical reinforcement learning and skill discovery. Then we will talk a little bit about some information theoretic concepts that will come in handy when discussing different approaches. And some of these concepts you might be already familiar with, such as scale divergence or entropy, but we'll go over them anyway, just to make sure that we're all on the same page. Then we'll discuss skill discovery algorithms. And once we kind of learn how we can discover skills, we'll also try to learn how we can use them and different options that we should consider there. And then at the end, we'll also talk about hierarchical reinforcement learning algorithms. All right, so let's start with discussing why skill discovery is something that is important. And so far in the course, we've been mostly in a scenario where the task was something that was given to us. And then we were trying to find a policy or come up with an algorithm that will be able to solve for that specific task. Right, and while this is a useful setting, it doesn't really cover everything that we might want our agents to do. So in particular, when you consider how we learn, it's not necessarily that we always get a goal or some kind of task that is given to us by somebody else and that we are trying to accomplish. We're also really good at coming up with our own goals and our own skills that we might want to practice. So we want to change the question that we're considering, and we would want our agents to also be able to discover interesting behaviors without any supervision. So in particular, I wanted to show you this little video of a baby left completely unattended in a room, and you can see that the baby is not given any specific goals, but it's still pretty good at coming up with the goals to practice, and through its own curiosity, it's not only coming up with them, but then it's also trying to practice them and it's trying to get better at all of them. So we want to get to a situation where we can leave a robot unattended in a room, and that robot will come up with anything that there is to do in that room that is interesting, and then we come back and the robot is capable of doing many different skills. Right, there's also a slightly different motivation, which is based on some of the research that comes more from neuroscience and biology. And in this particular paper that I'm citing here, researchers were doing a study on frogs, and they were trying to discover or trying to research what kind of how does the frog move and how does the spinal cord of a frog modulate all different behaviors. And what they found out is that there's a very small number of core skills that the frog knows about. And then the whole variety of motions that the frog can do comes from spinal cord just modulating these different core level skills. Right? So there's a small number of core skills, and these give rise to a large variety of behaviors. There's also a similar research in that vein that was done on human subjects, where the researchers were asking humans to grasp a large variety of objects. And then they would record the hand positions of the humans and try to do some analysis on that data. So they collected this big data set with many different humans grasping many different objects, and then they performed principal component analysis on the data set. And they noticed that with just a few top principal components, they can explain a huge majority of the data. So that also seems to point to something similar, where we have a small number of core skills or core behaviors that can then give rise to a large variety of things, of skills. So one other motivation for skill discovery is that maybe if we leave robots unattended and allow them to discover the skills themselves rather than us defining what they should be, maybe they will be able to come up with these core skills that then would allow us to generate all kinds of things. All right, there's also a much more practical motivation for skill discovery, or for skill discovery algorithms. And this is that so far we talked a lot about multitask reinforcement learning or meta reinforcement learning, and we always assume that we have a bag of tasks that we can pre-train on. Right? And once you start implementing these things, you very quickly realize that coming up with the task themselves is really tricky. And there are many different considerations that you have to think about while you do this. And very often it's just one of the limiting factors is that we are having trouble with coming up with a big enough set of tasks. And this might seem a little counterintuitive, so I thought maybe we can do a short exercise. So I'll ask you to write in the chat. You also feel free to raise your hand if you have any questions. I would like you to write down some task ideas for a tabletop manipulation scenario. And just to make it a little bit more specific, it's a tabletop manipulation scenario where we have a robot with a single arm that is in front of a table, and it can be given any objects. Right? So can you just write down any task that comes to mind, and just write as many as you can think of. Grab something, okay. Pick up, stacking object, picking up a spoon, okay. We got 3 pickups. Push down object from the table, pour milk into a cup, move the arm, dismantle the table. Whoa, that's a complicated one. Read the paper, okay, that would be interesting. Move to a specific location, pet a dog, rotate arm, solve chess, okay. Throw, do the harm shake. Yeah, that's a perfect one. Stand up using support. I'm not sure what do you mean by that exactly? Oh, I guess it's like it's a humanoid robot that needs to stand up using some kind of support. Take a port of table to stand. Oh, I see. Okay, great. Roll an object. All right. This is actually like a lot of really good ideas, and I might use some of these. So thanks a lot. These are great. All right. So I think one thing to consider here is that so we have a lot of things that are kind of close to each other, like picking objects or grabbing objects. But we have also a lot of things that are at very different levels of difficulty, right? We had, I think someone wrote to dismantle or assemble a table, right? So the difficulty of that task compared to just grasping something is very, very different, right? So when we come up with all the different tasks that we want the robot to do, we also need to keep in mind the practical algorithms that will try to learn these tasks. So we usually want to come up with a task that are feasible with our current RL algorithms that are at similar levels of difficulty, so that we can train all of them at the same time. And we also want to make them such that they share a lot of similar structures, so that if you train a lot of them, they can kind of benefit from all the other tasks. All right, so you were really good at this. I just wanted to mention that when we were going through that exercise, when we were developing the benchmark meta world, that was really, really painful. And it was really tricky to come up with this many tasks and do this such that each one of these tasks is feasible by a single task reinforcement learning algorithms. So especially when you work on these projects, use that creativity that you just displayed and come up with as many tasks as you can. And I think if you do this, the algorithms will become much better too. All right, so we talked a little bit about why skill discovery might be useful. So why hierarchical reinforcement learning? So far when we were talking about reinforcement learning algorithms, we were considering every single task to be at the same level of abstraction. So for example, if we're controlling the robot at a specific frequency, we'll be sending actions at that frequency. But we might want to ask the robot to do tasks at very different level of abstractions, right? We can, for example, we can tell the robot to go bake a cheesecake, but we can also be much more specific than that and say, well, first you need to buy ingredients, and we want to treat these two a little bit differently. Also, the first step to do that would be to go to the store, or to walk to the door, take a step, or contract a specific muscle. And we would want our algorithms to be able to reason on all these levels of abstractions, such that the lower levels can inform the higher levels, and we don't necessarily want to plan for baking a cheesecake by planning every single muscle contraction. We want to do it at much higher level. And these are the things that hierarchical reinforcement learning algorithms would allow us to do. In addition to this, it can be very useful with exploration. So when we are considering some tasks that can be much more long-term tasks, for example, block stacking, we don't necessarily plan in terms of contracting our muscles or how are we going to move our finger and so on, but we're thinking on much higher level of abstraction, where we're just thinking about the objects and where the objects should go. And this allows us to do this planning much more efficiently and allow us for better exploration. So we'll also use hierarchical RL algorithms to help us with that. All right, great. So this was a little bit of a motivation. Are there any questions at this point? Please raise your hand if there are any questions, or just speak up. All right. If not, then
there's a question in the chat. Does the human imposed hierarchy can the human imposed hierarchy potentially be suboptimal?
Yeah, definitely. I think so. So we will also learn about algorithms that try to learn how to do the hierarchy itself. So what are the low-level skills that it should learn, and the high-level skills that it should learn together with. So it will be kind of an end-to-end process that will learn both levels. There is still a little bit of human-imposed hierarchy or human-injected knowledge about, this being just 2 levels of hierarchy as opposed to many more, or maybe the task shouldn't have been solved in a hierarchical fashion in the first place. And I think this is a really interesting question as to how much is this constraining our algorithms as opposed to helping them. All right, so let's jump into some information theoretic concepts. So there will be a little bit of theory, but it should be relatively straightforward. And for some of you, this might not be new, and you might have heard about this before, but we'll go over this fairly quickly. All right, so first we'll talk about entropy. And in order to introduce that concept, we first need to talk about the distribution. So hopefully we are all familiar with distributions. And here we'll be plotting a distribution of a one-dimensional variable x. So on the x-axis, we have our different values that the random variable can take. And on the y-axis, we have the probability of the random variable taking that value. So then we can observe what kind of values the random variable takes. And then we can fit a distribution that has to sum up to 1 that corresponds to these events. So for example, a Gaussian in this case. All right, so this is what the probability distribution is. Now we'll refer to entropy as this script h, and it's an entropy of a particular distribution. And mathematically, it's defined as following. It's a negative log probability, log p of x, under the expectation of itself. All right, so what does that mean? So let's try to think about the terms that we have here. So that expectation here means that if we sample from our distribution, from our p of x, so we'll just sample according to this distribution. If the entropy is very high, then for the samples we sample, the log p of x should be quite low, right? So basically, if we want to maximize the entropy, that means we need to minimize this negative term here. So for the samples that we sample from our distribution, the probability mass shouldn't be that big. It should be as low as possible. So what does that mean in practice? So in practice, that means that if I sample something, that means that that sample doesn't carry a lot of probability distribution. So basically, it measures how broad our distribution is. If our distribution is much broader than something as picky as this Gaussian in the picture, for example, something that, let's say, looks like this, that means that we will have a lot of samples that we're likely to sample, for example, a sample here or a sample there, that don't have as much probability mass as they would have had if we sample something from a distribution that is much more peaky. Right? So if I sample something from a Gaussian like this, that means that the probability that so I'm very likely to get a sample that is close to that peak, and that sample will carry a lot of probability mass right here. Right? So basically, entropy is a measure of how random our distribution is, or how much randomness there is in that random variable. The other way to think about this is to think about it a little bit counterintuitively. So count as an entropy will tell us how easily can you guess what the sample will be. right? So let me give you a little bit better example here. So let's consider a Bernoulli random variable. So as if we were just doing a coin flip. And here on the x-axis, we'll be plotting the parameter of that Bernoulli random variable. So 0.5 means that heads and tails are equally likely. And on the y-axis, we are plotting the entropy itself. And here we can see that the entropy is the highest for the value 0.5. So what that means is that it's extremely hard for us to guess whether the outcome of that random event will be tails or heads if the parameter of the Bernoulli probability distribution would be 0.5. However, if that probability distribution, that parameter, the probability of getting tails, for instance, is equal 1.0, that means that entropy is very low. I don't even have to perform the experiment to know what I will get. Right? From the parameter itself, I can basically easily predict what's going to happen. So it measures a little bit how much randomness there is in that random variable. All right, so this is a little bit about the entropy. Let's talk about KL divergence. So you've heard a little bit about KL divergence, and we usually have been introducing it as a distance between two distributions. Right? So let's define it mathematically. So KL divergence is dKL between two distributions Q and P. It's a node-symmetric measure that is defined like this. It's an expectation under one of these distributions, under distribution Q, of log of the ratio between the two distributions. Log of the ratio between Q of X and P of X. Now, because these are logarithms, we can change it to look like this. So it's the difference between these two expectations. And then we can change it a little bit further and say that this is this negative expectation of the log P of X minus the entropy of Q of X. Right, so here I just use the definition that we just introduced, definition of the entropy. So I transform this term and put the minus in front of it so that it's an entropy. All right, so since this is a distance, let's first think about the simplest case where Q and P are equal to each other and whether the distance would be 0. And we can easily see, for example, from this part of the equation here, that this would be the case. So if P was equal to Q, or Q was equal to P, then that expectation would be equal exactly to this expectation, and then they will cancel each other out. This would be equal to 0. Right, so let's take a look at that final formula that we got here, and let's try to understand it a little bit better. And in order to understand this, we'll first plot some probability distribution P of X. And this is, let's say, some complex probability distribution that looks like this. Right? And now what we'll try to do is we'll try to find a probability distribution Q that is a Gaussian. We'll try to find the parameters of this Gaussian such that the KL divergence between Q and P is as small as possible. So we're trying to find a Q that minimizes that KL divergence that is defined here. All right. So because we're trying to minimize this, that means that we have to maximize the negative. So we're first maximizing this term right here. So let's just focus on that term. And for this term, in order to maximize it, we need to come up with a distribution Q that is extremely peaky here. So that if you sample from the distribution, so if we sample from our Q, this is the expectation under Q, the log probability of P of X would be as high as possible. So there's as much probability mass as possible. So this basically corresponds to a distribution that is very, very narrow, and then just looking, and it looks for a mode in the distribution P of X. Right? It's a mode-seeking behavior. Because if we put any probability mass for the distribution Q of X anywhere else, then the log probability distribution for that sample would be much smaller than it would have been for the mode. All right, so this is the first term. So it's a mode-seeking behavior that produces an extremely narrow distribution. And then we have the second term, which is the entropy of our Q of X. And we already learned a little bit about the entropy. So we are trying to make this entropy as big as possible so that the negative would be as small as possible. And that entropy will try to make the distribution wider. So we just talked about how entropy measures how broad the distribution is. So that entropy, if we try to make it as big as possible, it will transform our mode-seeking distribution into something that is a little bit wider. And here from this picture, you can see kind of the behavior that you will get if you're trying to minimize the KL divergence of this form with respect to Q. So you'll try to find the mode of the distribution, and then you'll try to blow it up a little bit so that it covers as much probability mass of P of X as possible. All right, so this is a bit about KL divergence. So let's introduce the last term that we might find useful in today's lecture, which is mutual information. So mutual information will denote with this script I, and is between two random variables, let's say X and Y. And mathematically, it's defined as following. It's a KL divergence between the joint distribution and the product of the marginals. So we can write it out fully like this. But instead of analyzing it in this form, I'll just try to give you two examples of what mutual information is. And then we'll change that formula a little bit to get more intuition of how we can think about mutual information. So here we have two random variables, X and Y, and we're plotting different samples from these distributions. And now what mutual information is trying to measure is how much is X dependent on Y and vice versa. So if you knew about X, how much would you know about Y? So in this plot right here, what we can say is that if we knew what value of X we had, then we can fairly confidently predict what Y we are going to get. The dependence between X and Y is very high. So this is an example of a high mutual information where X and Y are dependent on each other. Here in the bottom plot, the plot looks a little bit differently, where regardless of what value of X the random variable takes, Y is not really changing. So even if you knew about X, that wouldn't really help you in guessing what Y is going to be. So in this case, X and Y are independent, and therefore there's low mutual information between these two random variables. All right, so let's change that formula that we got right here to something that looks a little bit closer to what we've seen before. And in particular, this is actually a somewhat symmetric measure, and it tells you the mutual information is equal to the entropy of the first variable minus the entropy of the conditional distribution of P of X given Y. All right. So what does that mean? So we know intuitively that mutual information measures the dependency between these two variables. So let's try to analyze this. So mutual information will be high if that term is high. So that means that the entropy of P of X is really high. So you can't really tell what X you're going to get if you sample from this distribution. It's a very random distribution. It's very wide. So X on itself has high entropy, but then for the mutual information to be high, this term needs to be very low. Right? So that means that the entropy of P of X given Y needs to be very low. So if I just ask you to predict what X is going to be, you would have no idea. It would be very, very hard. But if I told you what Y you get to experience, what Y is, then you would be able to very confidently tell me what X is going to be. There's a high dependence between Y and X. So X by itself is very random, but as soon as you know about Y, you know what X will be. All right, so let's go through a little exercise to see whether this makes sense. So I'll give you an example of two random variables, X and Y, and I'll ask you whether they have high mutual information or low mutual information. So in the chat, you can just write high or low. All right, so here we go. We have one random variable that says it will rain tomorrow. It rains tomorrow. And then another random variable that says streets are wet tomorrow. So is it high mutual information or low? Yeah, okay, high. Great, yes. These are very dependent random variables. And basically, you can say that the entropy of whether it's going to rain tomorrow or not is actually fairly high. We have no idea whether it's going to rain or not. I guess maybe in the Bay Area it's a little different, but still. But if we knew that streets are wet tomorrow, it will be very easy for us to tell whether it's going to rain or not. All right, let's go for another example. So X is still it rains tomorrow, and Y is we find life on Mars tomorrow. Is it high or low mutual information content? All right, so it's fairly straightforward. Yeah, it's low mutual information because even though the entropy of P of X is still fairly high, we can't really tell whether it's going to rain tomorrow or not. The additional information that we're getting about Y that we find life on Mars tomorrow, it's not really going to help us guess whether it's going to rain tomorrow or not. All right, great. So this is a little bit more abstract. So I'll give you a particular example of mutual information that is actually used in reinforcement learning. And this is called empowerment. And the empowerment is mutual information between the next state and the current action. And so does anybody have any idea why this is called empowerment? Please just speak up, or you can write in a chat or raise your hand, whatever works for you. Right, any ideas? The current action basically determines next state, the impact of the action. Yes, exactly, right. So that means that the empowerment would be very high if your actions have a lot of control over the state that you're going to observe next. So if your actions are very powerful, if they have a lot of influence on the next state, that means that you're a highly empowered individual. All right, great. And a lot of people use that measure as something to optimize for, or something to measure how capable the agents are. All right, so we did a little review of some information theoretic concepts. Are there any questions at this point? All right, okay. So let's talk about some skill discovery algorithms. In one thing that we would want to do in skill discovery is to find algorithms that don't necessarily solve one particular task, but algorithms that can solve many, many different tasks, and they can come up with the tasks themselves. So one algorithm that goes towards this direction that we already talked about is a soft Q learning algorithm. And in soft Q learning, the setting we were considering was still where we had a task that was given to us, for example, a dog that has to come to the owner, but its behavior is a little more stochastic. It doesn't just go in a straight line, but it's a little more stochastic than that. In particular, the objective that the agent was optimizing looked like this. And here we had the additional entropy term that we just discussed. And then we had value and Q functions that we described, and then we had a standard Q learning algorithm, and we made some modifications to it, resulting in a soft Q learning algorithm that allowed us to be a little bit less committed than a standard RL algorithm would. And then we looked at some of the results here that allowed us to not be as committed to a single solution as you are, for example, in this case, where our policy is just picking the mode of our Q function and always trying to do those actions. And instead, we'll put a little bit of probability mass for our policy, even for the actions that are not perfectly optimal. Right, so this is something that goes a little bit in the direction we want, in that it can do more things than just one particular task, because at least it can do it in many different ways. Right, but this is not exactly what we need. Right? This is still a little bit different. So what we would need, that would be a policy that would have a form that would look something like that. So it would be a policy pi of a given s, as we usually do, but it will be conditional on one additional random variable, and that random variable will denote as task index or some kind of skill index. So we want the agent to do different things depending on the value of z. And that z could be just an integer. So for instance, if we have an agent that is performing different tasks in this little grid, that the agent starts right here in the middle of it, then with different z's, we would want the agent to go to different places, or to visit a different part of the state space. So for example, if our z is equal to 0, maybe the agent would move up. If z is equal to 1, it will move to the right. If it's equal to 2, then the agent would explore this bottom right corner. 3 would be a different trajectory, 4 a different trajectory, and 5 would be a different trajectory too. Right? So we want the agent that will we want a policy such that with different task indices, that policy will do completely different things. And we can't really use just max entropy RL to learn something like this, because first of all, action entropy is not the same as state entropy. So we can have an agent that can act very differently in a specific state. It can take very different actions, but that doesn't necessarily mean that it will land in different states. It can land in very similar states. And in addition to this, our maxed entropy policies, so the soft Q-learning policies, are stochastic, but they're not controllable. So we can't very easily pick what kind of solution we want. Versus here, we would want to have a full control through our Z variable to tell the agent what kind of skill, what kind of task we wanted to perform. Right, so intuitively what we would want is something that results in low diversity for a fixed Z. So if I told the agent what kind of task index I want, we want the agent to know what to do. But then high diversity across different Zs. So if I didn't tell what Z I want, we want the agent that can visit any part of the state space. All right, so the intuition is that different skills should visit different state space regions. So let's try to come up with an algorithm that could do something like that. So in order to do this, in order to learn this policy, we would need to learn some kind of reward function that is fully automated. So that reward function will be, in addition to being conditioned on the state, it will be also conditioned on the skill itself. Right? So given what skill you're doing, the reward function will be a little bit different, but we want it to be automated. We don't really want to come up with that reward function for every single task that we have, that we hand engineered, but we want the agent to discover the Z itself and then have the automated reward function for that specific Z. Right? And then the objective of the agent would be to just maximize the reward, that automated reward that we haven't come up with yet, across all the different Zs. All right. So here's one idea how we can do this, what we can propose for that reward function. So we'll reward the states that are unlikely for other Zs. And so what does that mean exactly? So if our reward is rewarding every state that the current Z can visit, then none of the other Zs can, then that would mean that we are covering the state space fairly well, and that skill is fairly distinct from all the other skills. Right? So if, for example, our Z was equal to 2, let's say we would want the agent to discover this part of the state space, and this is a different part of the state space that the agent would have discovered if had we given it any other Z, any different Z. So either this one or that one or so on. All right, so that idea, at least on the surface, kind of makes sense. So how could we formalize it a little bit more? Right, so we want to reward the states that are unlikely for other Zs. So here's one proposal, what we can do. We can learn a classifier that, given a state, tells us what Z could have resulted in us visiting that state. Right, so we can easily train a classifier like this. That classifier can be trained using supervised learning, and it will be just looking at the states that a particular skill has visited, and it will try to regress towards that skill. And then we can have the reward function that tries to help this classifier as much as possible. So it tries to make the skills a little bit more diverse, such that this classifier have a very easy job. Right, so let's go through a little example so that it makes a little more sense. So in the standard RL setting, we'll have the policy that produces actions in the environment and then gets a state as an input and kind of keeps going. Here we'll have an additional input, which is the skill that we're currently doing. But we'll also have this discriminator, this classifier that, given a state, will try to tell us what Z could have accomplished that state, could have ended up in that state. And these two will be interacting with each other. Right, so in practice, it would work like this. We would start with sampling 2 different Zs and giving it to our policy, and we'll get 2 different trajectories. So let's say the trajectory in green was produced for Z equals 0, and the trajectory in blue was produced for Z equal 1. And they're very close to each other, but they're slightly different. So now in the next step, we'll try to learn a classifier that tries to learn a decision boundary between these 2 trajectories. So it's trying to do the best job it can. These trajectories are fairly entangled, so it's a little tricky, but it's trying to separate the green trajectory from the blue trajectory. And let's say it came up with a decision boundary that looks like this. Right? That's not really perfect, but it's the best job it could do. Right? So now we have a policy that given that classifier is now this discriminator is now trying to help it. Right? It's trying to make the next iteration for it a little bit easier. So given the decision boundary, it will try to produce the trajectories in the next generation that will make the current classifier a little bit better, because we are rewarding our policy for maximizing the log likelihood of that classifier. Right? So it will produce two trajectories that are more different. And then we'll do another iteration of the classifier. So the classifier will learn a little bit better decision boundary. And then we'll continue doing so. So then our policy will try to help the classifier again, and we'll produce trajectories that are even different, and then we'll get better decision boundary, and so on. All right, so overall, we see that there's this two-player game where both players are going towards the same goal, where the discriminator is trying to do the best job possible in trying to classify which skills would produce certain states, and then the policy is trying to make the classifier's job as easy as possible. So does that make sense? Are there any questions at this point? All right. Okay, so let's look at some examples of an algorithm that does exactly this, and let's try to see what kind of task it can learn. So first, the authors try this algorithm on a cheetah task, where we have a cheetah that usually the task of the cheetah is to run forward as fast as possible, but here the only reward that is optimizing is trying to help that classifier. So it's trying to produce skills that are as diverse as possible so that the classifier has a very easy job. And here are some examples of the skills it came up with. So one of them is cheetah running forward, but then we have some other skills such as cheetah doing backflips or cheetah running backwards. Here's also a different environment using exactly the same algorithm, where we have the ant that is trying to learn a whole bunch of different behaviors by optimizing this diversity objective. And here we have a particular example of a mountain car, where one of the solutions that is just comes out from this diversity objective is actually to just solve the task, and this is the one in the at the very top. All right, so we discussed a little bit the intuition behind this, why we would want to come up with a classifier and so on, but we also introduced this concept of mutual information. So let's try to see if there's some connection between the algorithm that we just developed and the concept of mutual information. So this is, so far here, what we've written here is everything that we discussed so far. And let's consider a specific mutual information, which is the mutual information between our skill index or task index and the current state. Okay. Using the definition of mutual information that we talked about, it would look like something like this. And now the first term will be maximized if we are just using a maximum uniform prior over our skills. So basically, if we want to maximize the entropy over Z, that means that we need to be able to sample every skill with the same probability. So if our Z is just a categorical random variable, it should be distributed uniformly such that every skill has a chance to go. And then the second term here is minimized by maximizing our log probability of P of Z given S. Right? So this is by maximizing our classifier, by trying to help our classifier as much as possible. Right? So that basically says that given the state, I should be able to tell what skill produced that state. Right? And our policy is trying to minimize this term by maximizing that log probability of the classifier. All right, so this is a skill discovery algorithm that was trying to discover skills that are as diverse as possible, and they might not be very useful, but at least they try to cover as much of the state space as possible. Are there any questions at this point?
There's a question in the chat that's asking, is there an optimal number of Z that covers the entire state space while not overlapping between different Z? Right,
so the overlapping part is hopefully taken care of by the algorithm itself. So regardless of what the number of Z's is, the algorithm will try to, as long as you sample them uniformly, the algorithm will try to cover or make sure that they don't overlap with each other. Now, is there an optimal number of Z's to cover the entire state space? I think this is a very tricky question, and we don't really have an answer to this. We would need to have some kind of way of describing a state space in a way that we can discuss its coverage. And overall, I don't think we have an answer to this. So in practice, what we would do is we would set Z to be a categorical random variable that can take values from 1 to a big number, and then we'll see what kind of skill it produces. But I don't think there is any, or I haven't seen any research that has been done on what kind of, how big the Z should be to cover the state space. I think this is a very good question, but very tricky to answer. All right, thanks. All right, so now let's talk a little bit about how we can use these discovered skills. All right. So far we discussed that how we can learn a policy that given different Z values, that could be just integers, will produce different behaviors. But we don't want to just learn a diverse set of skills. We want to learn them such that we can then later use them to do some kind of task. Right? So for example, we might want to learn some kind of way of using them such that we can perform a navigation task where we have that ant that has to navigate to different points. Right? So one question is, how can we use the learned skills to accomplish a new task that is given to us at test time? Are there any ideas here? Please raise your hand or write in the chat. So just to repeat the question, we have a low-level policy that can do different things depending on the value of Z. Right? So for different Z's, it will do very different things. Now we want to find the policy that is able to reuse these skills to do a particular task. All right, we can optimize the Z sequence. Right, yeah. Okay, so we can learn another policy on top of it that operates on Z's, right? So now instead of the standard actions being our actions A, that policy will be optimizing for the perfect Z sequence to accomplish a new task. Right, and this is actually what's done in the paper that we were just discussing, which is called Diversity is All You Need. It was written by Ben Eisenbach et al. And they try to then repurpose the skills that they already learned to learn tasks that are kind of more useful. And they show results showing quite convincingly that you can learn a policy, a high-level policy that operates on those Z's, and it can find what's the best way to use these skills to accomplish a particular task. All right, so this seems like a good idea. This could work, but can we do better than this? Right. And when we think about how we could do better, let's try to think a little bit what are the problems with this solution. So one problem that we can see is that the skills that the algorithm comes up with might not be particularly useful. So it might be just an ant, doing kind of random motions, random motor babbling. But as long as that behavior is different than any other behavior, it will still be perfectly acceptable. But it won't be really useful for something that we might want the ant to do a little bit later. And then in addition to this, if you think about learning an additional policy that operates on these latent variable Z's, on these task indices Z, it's not very easy to use these learned skills, right? We need to run another reinforcement learning algorithm that will learn that policy, and that will take many samples, and the route is tricky in general. So it's not that you can just very quickly use these skills straight away and kind of be done with a new task. Right? So we'll start with focusing on that first question right here, that skills might not be particularly useful, and try to think of ways how we can make them more useful. And then we can see how that results in a partial answer to the second question as well. Right, so here's a question to you. What do you think makes a useful skill? So right now we're just coming up with very diverse skills. How can we constrain this a little bit more and say that skills have to be useful? And please remember that we don't have access to any tasks. Right? We're doing this completely unsupervised, where the agent has to discover the skills themselves. Are there any ideas what makes a useful skill? Please write in the chat or raise your hand. And this is actually a very tricky question, so don't feel bad if you if there's nothing that comes to mind. But I'll give you another 30 seconds or so. State action spaces are different from other skills. All right, yes, so state action spaces are different from other skills. This is similar to the objective that we had before, where it's optimizing for diversity of skills, right? So as long as they're diverse, they should be useful. That's a very good objective, and it results in a useful algorithm that we just saw. But can we do a little bit better? Can we make the skills more useful? They can be combined to something. Okay, that's a really good idea. Maybe the skill is performed over and over during the optimization process. Skills that utilize different parts of motions. Okay, yeah, I think there's some good ideas here. Right, so let me try to convince you to one particular property that would help us to make skills a little bit more useful. And I want to show you two examples of things that are not necessarily very useful. So we have an ant that is doing kind of random motions, and it's not really clear what's going to happen. And then we have this this kid that is playing with Jenga, and also the consequences are kind of catastrophic, but more importantly, it's kind of very tricky to predict what's going to happen. And then here are some examples of skills that are very useful, right? So at the bottom, we can see the ant that is just running forward as fast as possible. And up top, we can see this cartoon character juggling really well, right? So I'll make an assumption that what makes a useful skill is how hard or how easy it is to predict the consequences of performing that skill. So the skill won't be useful if the consequences are very hard to predict. And we'll assume that the skill is useful, so you are more skillful if the consequences of performing that skill are very easy to predict. So this might sound a little, not very straightforward why that is, but let's just run with it and kind of see what happens if we do that. All right, so we want to bake in that notion of predictability to help our skills to be a little bit more useful. And in order to do this, we will introduce a slightly different mutual information. So before, we are optimizing mutual information between our task index or the skill index and state S. Now we'll be introducing a slightly different mutual information that is a conditional mutual information. And very quickly, just to tell you what conditional mutual information is, this was the definition of our original mutual information. Now the conditional mutual information is just we condition everything on the conditional variable z, for instance. All right. So the particular mutual information that we'll be looking at is the conditional mutual information between the next state given the current state and the z given the current state. All right. We can write it out like as this. Now, what does this mean? So we have the first entropy term that is telling us that we want the entropy of S prime given S to be as high as possible. And then we have the second entropy term that tells us that we want S prime given S and the skill that we're doing to be as small as possible. So the first term corresponds to a future that is very hard to predict for many different skills. So if we don't know what skill you're performing, if your start at a certain state S, it will be very hard to guess which state you're going to go to next. So we don't know what skill you're performing, it's very tricky to tell what's going to happen. But as soon as we know what Z is, it should be very predictable. It should be very easy to tell which state you're going to end up in for a given skill. All right. So this kind of includes that notion of predictability because we have that S prime here. So it tells us a little bit about how predictable is the future. And we can write it out mathematically, and doing a few approximations for you, the result looks like this, where we have the numerator that we're trying to maximize, which is this, we're trying to find the log probability of this Q phi S prime given S comma Z. So we want deadlock probability to be as high as possible. So given skill, we want the future to be predictable. And then in the denominator, we would have something that we're trying to make as small as possible. And that means that for all the other skills, it should be very hard to predict what S prime is going to be. All right, so what you can see here is that we have this term and also this term here that is a probability of S prime given S comma Z. Right? So this is something that we need to learn here. So let's think a little bit about what this is. So this is the term that we are considering. And if you look at this, this actually reminds us of a term that we've seen before, which looks like this. So this is a very similar looking term, except instead of Z's, we have A's. And this term was what we call the transition model or a dynamics model that we're trying to learn, for example, from model-based reinforcement learning. Now the term up here is very similar, except it's not taking actions as input, but it's taking the skill Z as input. Right? So this is kind of like a dynamics model, but not for an action, but for an entire skill. So it's trying to tell us, given the specific skill, what is the next state that I'm going to end up in. And now there's one particular aspect of this that makes it a little bit easier, which is our skills, our Z's itself, are also trying to help this model in a similar way how we were trying to help our classifier before. Now our skills are optimized to help this model as much as possible. So skills are optimized specifically to make the skill dynamics, so they're trying to make learning of this model as easy as possible. So what that means is that hopefully our skills will avoid situations where it's very hard to predict what's going to happen next, because if you're just doing random motions, it might be really hard to predict what's going to happen. And they will focus on things that are very easy to predict, so that the learning of the skew is as easy as possible, and that would correspond to skills that are a little bit more useful, such as running forward. All right, so summing all of this together, we arrive at an algorithm called DADS that was introduced by Archie Sharma et al. And the algorithm works as following. So we first initialize our policy, and we initialize our previously what we discussed as a classifier, now is the skill dynamics model, Q5. Now we sample a skill from some prior distribution, and that prior distribution should be as uniform as possible. In this case, I drew it as a Gaussian, but it could be just a uniform distribution. We sample those skills, and then we collect M on policy samples. So for given every Z, we'll give it to a robot, and we'll tell the robot to do something according to that Z. Now, once we have these trajectories, we can now update our skill dynamics model Q, given that data, right? So this is similarly to learning a dynamics model, just in the skill space. And then once we have that model, we can now compute the reward, because that reward is based on that model. Okay. So we compute the reward, and once we have the reward, we can update the policy given the state transitions that we got and the reward that we received for them. So, and we can do this using any RL algorithm, and I believe that in this paper, the authors used the SEC algorithm to do that. All right, and then we do this repeatedly in the loop until it converges. So we get a policy now that does different predictable things for different Z's, and then we'll do another set of rollouts, and we try to move towards that direction again. All right, so in terms of some results, so first, if we look at the trajectories that an ant robot is producing compared to diversity is all you need, so here's a plot of trajectories that you get if you set different Z's for diversity all you need or Diane. So they're a little bit messy, but they still result in different behaviors. However, if you do it for DATs, these trajectories are kind of much more consistent, and they go in very different directions. So it's a little bit less messy. And we can see very similar results on the humanoid, where it's just a much more complicated robot, but it's still kind of very consistent in what direction it's trying to go. And the skills are a bit more useful because they're trying to be predictable. All right, so So far, we changed the algorithm a little bit so that we'll have skills that are more predictable. So how can we use these learned skills? And as you've also learned about this a little bit in the model-based RL lectures, where once you have the model, you can use that model to do model-based planning. So here we can do something very similar, just use skill dynamics for model-based planning instead. And we can do this using any model-based planning technique. And what that usually corresponds to is us sampling different Z's, different trajectories of Z's, then doing imaginary rollouts using our model, and then seeing what kind of reward we are getting for each one of these trajectories, and then updating our planner based on that. So that's really important, because what that allows us to do is that because we have that skill dynamics model that we use for something, something a little bit different, but now this model is very useful to also learn something at test time where we don't need any additional rollouts. Right? We can use just model-based planning and this skill dynamics to do imaginary rollouts, and based on this, we can figure out which skills we should use and how we should compose them such that we can accomplish a new task. All right, but here we are planning for skills rather than for actions, and that also means that our task can be learned zero-shot, so we don't need any additional data. And the others show some results indicating that that's possible. So the result that I showed before of an ant navigating to different points on that board actually comes from this paper, and it was learned without any additional data. And the same can be done for a humanoid as well. All right, so to summarize that part, we talked about two different skill discovery algorithms that use some form of mutual information. One of them, the DATS algorithm, uses predictability as a proxy for usefulness of a skill. And then that particular method optimizes for both predictability of the skills as well as for diversity. And it allows us to do model-based planning in skill space. And more importantly, the family of skill discovery algorithms is actually quite large, and there are different papers that talk about this. And one exciting part about this is that not only we can discover new skills now, but we can also apply it to something like meta-reinforcement learning, where it opens up new avenues. So we can potentially do meta-reinforcement learning in a way that is completely unsupervised, where we first kind of run a skill discovery algorithm to discover skills that are useful, then we meta-train on this, and we kind of keep going. And this is described a little bit more in this paper by Abhishek Gupta et al. On unsupervised meta-learning for reinforcement learning. All right, so that summarizes the skill discovery part of the lecture. Are there any questions at this point?
There are a few questions in the chat. The first question is, how do you optimize Q5?
How do you optimize Q5? Right, so this is a supervised learning problem at this point, similarly to how we were training the classifier before. Now Q5 is the skill dynamics model that is trying to predict the next state given the current state and the Z. So we have all three of these, right? We have the next state from our rollouts, we have the Z that we send to the robot, and we have the state that the robot was in. So we can perform supervised learning. We can apply supervised learning to this problem to learn that model as well as possible.
The next question is Q of S prime given S comma Z similar to the measure of empowerment, but taken over a horizon with actions induced by Z?
Right, yes. So there is a very strong connection between the empowerment and the measure that was introduced here, except here we are operating on Z's rather than on actions. And I encourage you to take a look at the DATS paper. In the appendix of the paper, there's a little bit of motivation behind this, and kind of they describe the connection to the empowerment as well. Can you learn skills that are not locomotion, for example, for object manipulations? Right, so it's a very interesting question. So usually these skill discovery algorithms have been shown on things that are things such as locomotion, where it's relatively easy to come to a useful skill, right? So for an ant, for example, as soon as you start moving in a certain direction, that produces some kind of diversity, and that skill is immediately useful because then you can use it for navigation. With manipulation, the problem becomes a little bit more tricky because for us to discover a useful manipulation skill, you probably need to be very targeted and go to a specific object and do something with that object and so on. And these tend to be much more difficult than something like the locomotion scenario. So I haven't seen many examples of these algorithms being applied to manipulation skills, but I think this is a great open avenue for research and for future work. Is there a way to reduce similarity of skills, learn movement and rotation instead of many similar types of movement that work in slightly different directions? I see. Is there a way to reduce similarity of skills? Right. So if I just go back in the slides real quick, when we were introducing the DATS algorithm, we were learning a particular classifier that was looking at this right here, this log of P of Z given S, and this was given the current state. It turns out that you can condition it on many different things. It can be not only the current state, but it could be the full trajectory, for example, of all the states that that skill visited, or it could be just the final state that it ended up in. And the resulting trajectories, the diversity of these trajectories will be a little bit different, right? So you would measure their diversity with respect to the entire trajectory rather than a single state. And one particular version of this is introduced in this paper called Variational Intrinsic Control. But I guess overall, by controlling what this classifier takes as input, you can control the diversity, the resulting diversity of the skills. All right. So let me just get back to where we were. And I wanted to also talk a little bit about hierarchical reinforcement learning. So far, we talked quite a bit about how we can learn skills and then how we can use these skills by a high-level policy. But we don't necessarily need to discover these skills in order to have this hierarchical structure where the high-level policy is able to use some low-level skills. So let's talk about that. So we talked a little bit about why hierarchical reinforcement learning might be useful, how it will allow us to perform tests at various level of abstractions, and how it can be useful for exploration. And hierarchical reinforcement learning is a very vast field, and it would be really tricky to kind of introduce all the different works that were that people wrote about hierarchical reinforcement learning. So instead, I wanted to show a few axes on how you can design a hierarchical reinforcement learning algorithm, and then show you examples of that. And then we'll, based on each example, we'll be trying to say what kind of design choices the authors took. All right, so let's build a standard hierarchical reinforcement learning algorithm. And it looks something like that. So we have a low-level policy pi L, and this is a standard policy that we will learn in a standard flat reinforcement learning as well. It interacts with the environment, it takes a state from it, and then produces a certain action that goes into the environment, then gets the next state, produces the next action, and so on. Right, so far, this is just a standard reinforcement learning. Now we'll introduce another policy, a high-level policy, pi H. That policy will take the initial state, and that policy will command the low-level policy. So in particular, it will send a command Z1 in this case, and that command will stay constant for a certain period of time. Right? So the low-level policy is kind of getting its goal from the high-level policy, and it's the same goal for a number of time steps. Then after the low-level policy is done, we'll take the next state. The high-level policy will receive that state, and then it will do it again, but it will send a different command to the low-level policy. Right? All right, so there are now a lot of design choices that can be made here. So first, the command that the high-level policy is sending to the low-level policy can be a goal that is defined as part of the state space or not. So that means that the low-level policy can be either goal condition or not. So if it's not a goal condition, we can be sending kind of any command that then the low-level policy needs to learn how to interpret, such as maybe a natural language command or some kind of latent space that the low-level policy initially has no idea about, but over time it can figure it out. or we can send the goal that we want the policy to reach. And this is the goal that is expressed in terms of the state space of that policy. And if we do that, we can apply things such as hindsight experience relabeling that we talked about before. All right, so this is one axis. Then the second design choice that you can make is whether the low-level policy is pre-trained or whether everything is learned end-to-end. All right, so you can either train the low-level policy first, and this can be trained without any knowledge of the high-level policy, or you can train all of this, given that hierarchical structure, all at once in an end-to-end fashion, and then you will get both the low-level policy and the high-level policy. All right. So then we have the third design choice, which is whether the low-level policy is self-terminating or whether it's commanded at a fixed rate. So in that example that I showed here, we would maintain the command that is being sent from the high-level policy over 3 time steps, and after this, that's kind of it. At this point, the low-level policy ends, and the high-level policy gets to send the next command. But we can also imagine a different scenario where the low-level policy keeps going and it tries to accomplish this goal up until it decides that it's done. It can self-terminate, right? And the fourth design choice is that this is kind of similar and applicable to a standard reinforcement learning. This can be learned on or off policy. All right, so we'll discuss we'll see a few examples of hierarchical reinforcement learning algorithms, and I'll go over them fairly quickly. I'll show you some screenshots from the papers and discuss the results and the design decisions, and then I'll ask you what were the specific design choices along these axes that the authors took, and we'll see if you can guess it right. So first, let me do this example myself so that we can kind of see what this game is about. So here we have our algorithm that we just discussed. This is the DATS algorithm, where we discover the skills and then we can use them using model-based planning. So in this case, the design choices that the authors made were the low-level policy is not goal conditioned. We were learning that latent space Z, that was not a specific goal in the state space. The low-level policies were pre-trained. We were particularly using a different algorithm to learn these skills, and then we can learn another policy on top of it or use model-based planning to do high-level policy. The authors were actually performing them at a fixed rate, so they were not self-terminating, and everything was being learned on policy. We didn't discuss that, but that's if you read the paper, you will see that. All right. So let me introduce the first hierarchical RL work, which is called Learning Locomotor Controllers. This was written by Nicholas Hess et al. Here's a screenshot from the paper that shows the structure of their hierarchical policy. So let's look a little bit closer at this. So first, in this blue box, we have the high-level controller, and this is a recurrent neural network that maintains this state ZT. And then we have a low-level controller, which is that policy in green here, right? That block in green. Now, the high-level controller is sending a command called C to the low-level controller, and it's doing it every k steps. So in that particular diagram, k is equal to 2. So it's sending that command here, and then the same command is sent to the next time step, and that's it. At this point, it ends and kind of does it again in a second. Then we have proprioceptive information that is given both to the low-level and the high-level policy. But the high-level policy has this additional privilege information about the task that the low-level policy doesn't get to see. All right, a few more facts about this paper. Both the high-level policy and the low-level policy are trained separately. They first train the low-level to do a whole bunch of different things, and then the high-level to operate on this. They're both trained with policy gradients. And they use what they refer to as hierarchical noise to do exploration for the high-level policy, where the high-level policy is just sending noise commands initially to the pre-trained low-level policy to do better exploration. And here's a video of showing some results where we have this snake-like robot that when you modulate it with this high-level noise from high-level policy, it kind of does sensible motion. And then if you send noise and it does something sensible, you can learn a policy a high-level policy on top of it. And here's one example of that policy navigating to a specific, navigating the snake robot to a specific location on the board. And then it can also do something a little bit different, such as this Canyon traversal task. And then they show some results showing how important it is to pre-train the low-level policies, and they show how much better this algorithm is compared to the baselines. All right, so now the question to you about the design choices that were taken, that were made in that for this algorithm. So is it a goal condition? Is the low-level policy goal condition or not? And please just say 1 or 2. So 1 would mean it's goal condition, 2 would mean it's not. And you can just write in the chat. 1, 2, 1, 2. All right. Okay, so it looks like it can be a little confusing. So in this case, this is not goal condition. So the high-level policy, we didn't discuss it that much in detail, so I totally understand that you might be a little confused here, but the high-level policy is not sending goals, it's just sending some kind of command C that then the low-level policy needs to interpret. All right, is the low-level policy pre-trained, or are they both learned end-to-end? Again, write 1 or 2. So 1 is pre-trained, 2 is E2E. 1, mostly ones. There was a 1, 2. Yes, they're trained separately. So yeah, low-level policy is pre-trained. All right, next question. Is the low-level policy self-terminating, or is it commanded at the fixed rate? Fixed rate 2, 2. There's some ones. Yeah, okay. Yeah, it's commanded at the fixed rate. We talked about k equal to 2 for that specific diagram. And is it trained on or off policy? Again, 1 or 2. 1, 1, 1, 1. Okay, this is fairly straightforward. Yes, it was trained with policy grade and on policy. All right, great. Let's jump to another paper. So this paper is called the Option Critic Architecture, and this is written by Bacon et al. And this introduces a notion, so it actually doesn't introduce it, this concept was known for quite a long time, but it applies it to this modern deep reinforcement learning scenario. And it's a concept of an option. So an option, here depicted by omega, is a triple that consists of this variable I omega, pi omega, and beta omega, where I is the initiation set of the option. So it tells us when the option is allowed to start. Pi is an intra-option policy, so it's a low-level policy that gets to act for a specific, for in that particular state. And then beta is a termination function. So beta is a function that, given a state, can tell can allow option to tell whether it should terminate or not. Right. So the option itself decides when to terminate. And they use this particular diagram that shows our standard MDP setting where different actions led to next states. But then it also shows how this works with options, where at any given state, an option can decide that this is now a time for this option to go. And that option can make this larger jumps. So this is some low-level policy that doesn't just go to the next state, but it can take a larger jump and do a few actions to get to the state that's a little bit further away, and then do this over and over again. And then it also decides when to terminate. Right? They also show this diagram to show more or less how this works. So we have an environment that gives you a state, then that state is taken by different policies for different options. And then we have an addition policy over options that then decides which option gets to go. All right, so a few other things from this paper. So option is a self-terminating mini policy. They train everything together with a policy gradient algorithm. Oh, and that's it. All right, so to show a few results. So here they show the termination state frequency. So they basically try to depict in which states do the options terminate. And you can see that in this grid scenario, they very often terminate close to the exit, which kind of seems to make sense. So that probably means that we have an option per room, and then this option decides to terminate when it's close to the door. And then they show some results on the Atari benchmark showing that this hierarchical option critic algorithm is better than a flat RL algorithm. All right, so let's do the quiz again. So what are the design choices that the authors made here? So first, is the low-level policy goal condition or not? 1 or 2? 2. Yep, that's not a goal condition. Are the low-level policies pre-trained or are they trained end-to-end? Okay, 2. Yep, they're trained end-to-end. Great. Is the low-level policy self-terminating or fixed rate? 1 or 2? 1. Yep, it's self-terminating. That's what the option is. And is it trained on policy or off policy? And the answer is on the slide. Yes, it's on policy using policy gradient. All right, let's go over 2 more algorithms real quick. So first, let's talk about relay policy learning. This is an algorithm introduced by Abhishek Gupta et al. And here we have a diagram that looks very similar to the diagram that we see on the right, with one distinction, which is that the high-level policy is sending goal states as opposed to some high-level commands to the low-level policy. All right. In particular, the way that the authors trained this algorithm is by pre-training it with user demonstrations. And they ask the user to do all kinds of different things in a kitchen environment. And these are not tasks. They're just asking the users to kind of play in that environment, and that's it. Once they have these demonstrations, they do heavy data relabeling. And they have a goal condition high-level policy, as well as goal condition low-level policy. And now you can do hindsight experience relabeling for both of these levels using the algorithm that you learned about previously here. Then they do imitation learning using those relabeled demonstrations, and then they continue with reinforcement learning fine-tuning. So a few more facts. These are goal condition policies, both on high level and low level, that are trained with relabeling. They use demonstrations to pre-train everything, and everything is trained using an on-policy algorithm. And some results. Here is a long horizon goal on the left that they want the policy to achieve, and they show how their policy is pretty good at performing this task compared to other baselines. And then they also show results indicating how useful it is to pre-train it from demonstrations. All right, so again, quiz. Design choices. Is the low-level policy goal conditioned or not? 1 or 2? 1. Yeah, great. It's goal conditioned. Is the low-level policy pre-trained or is everything trained end-to-end? Now, this is a little tricky. Great, yeah. So there are a few 2s, but yeah, it's trained end-to-end. So both of them are trained at the same time. It's pre-trained in the sense that we're using demonstrations first, but it's not that we're training the low-level and the high-level policy separately. They're trained at the same time, and that's what we meant by pre-trained versus end-to-end. Now, is it self-terminating or are the goals commanded at a fixed rate? We didn't talk about it explicitly, so it might be a little tricky, but take your guess, 1 or 2. Okay, we have a few 2s, we have a few 1s. In this case, they're being commanded at a fixed rate. That's what we use for relabeling. And then is it trained on policy or off policy? Right, everybody's saying correctly. Yes, this is trained on policy. All right, so let's introduce the last reinforcement learning algorithm called Hero. And this is very similar to the algorithm we saw before. And here is a diagram from the paper. High-level policy is sending goals to the low-level policy. They're commanded at a fixed frequency. And the only difference is that this algorithm does this hierarchical reinforcement learning, but it does additional relabeling that allows it to perform this using off-policy reinforcement learning algorithm. So in particular, what it does, it changes the way that the high-level policy operates, because when the high-level policy commands a certain goal, the low-level policy will try to achieve it, and then it will achieve a goal that is slightly different. Now, when you get that experience, you need to accommodate for the fact that the low-level policy has changed in the meantime, so you need to perform some kind of off-policy correction, and that's what they introduce in this paper. So they work with goal condition policies with relabeling. They do off-policy training through off-policy corrections. And then here are a few results. So here is a robot that learns how to push this block to a goal location. And they also perform, in the follow-up paper, they perform similar tasks on the real robot. And they show how their algorithm is able to beat most of the baselines. All right, so the last quiz of today. What were the design choices that were made by the authors? So is it the goal condition or not? 1 or 2? That's all goal condition. Great. Is the low-level policy pre-trained, or is it all trained end-to-end? Yeah, a lot of 2s. Yes, this is end-to-end. Now, is the policy self-terminating, or is it being commanded at a fixed rate, 1 or 2? 2s. Yeah, we saw at least 1, 2. Yeah, a few 2s. Yeah, great. It's commanded at a fixed rate. And is this an on-policy or an off-policy algorithm? 2, we see a lot of 2s. Yes, it's an off-policy algorithm, and it introduces off-policy correction that allows to do this. All right, great. So to summarize that part of the lecture, when you do hierarchical reinforcement learning, there are multiple design choices and multiple frameworks to use, and these are just 4 particular axes that I picked that we're kind of iterating over, but there are many more. It usually helps with exploration and temporally extended tasks. It can be a little tricky to get it to work, to get hierarchical reinforcement learning to work, because now you kind of, a standard flat reinforcement learning algorithm is difficult to get to work. Now you have to do kind of policies at 2 different levels, which can be quite tricky. And it also seems like a natural direction for harder reinforcement learning problems where you might want to deal with longer horizons and so on. And in particular, if you'd like to get a little bit more kind of common sense of how these algorithms work and why they work, I recommend this paper by Ophir Nahum et al. On why does hierarchy sometimes work, where they show some experiments kind of disentangling what makes it useful and what doesn't. Right, so we're out of time. So we discussed today information theoretic concepts. We talked a little bit about skill discovery algorithms, how we can use these skills, and then how we can apply similar concepts in a hierarchical RL scenario. And next week, we'll talk about agents that can learn, sorry, not next week, but on Wednesday, we'll talk about agents that can learn continuously over their lifetime. And this is it. Are there any questions?
There's a raised hand from.
Yep.
I have a question, is 2 levels are standard in hierarchical learning, or like people have explored more levels, and how does they work or not?
Right. I think there are some papers that try to do more than 2 levels. I think usually in practice, 2 levels are already pretty hard to get to work, given that the low level is constantly changing and the high level has to kind of accommodate for this. And because these algorithms maybe haven't worked as well as everybody expected, at least to this point, people haven't really, it's not a very common thing to do to try more levels than 2. But I think it could be an interesting idea or area to explore.
Thank you.
Mm-hmm. Are there any other questions? There's a question from.
Yes, so I have a question. So I guess these kind of 2-level systems also have the problem. So when you train end-to-end, there is a problem that is inevitable to face, which is the chicken and egg problem. So the low level depends on a good high-level agent, and a good high-level agent depends on a good low-level agent. So how is this able to prevent this problem?
Yeah, this is a really good question. Thanks for asking. Yeah, so this is a common failure mode in many algorithms, especially for algorithms that make design decisions that make these problems more apparent. For example, in the option framework, since these low-level policies can also learn to self-terminate, a common failure case is that an option would only act for one time step, in which case it's not really an option, or there will be only one option for the entire task, in which case it's also kind of doesn't make that much sense, because we want to have this like particular structure where we can split the task into a few options, but not just have one task be one option. That doesn't really simplify the problem. There are a few design decisions that make this problem a little bit easier. So for example, if you command agents at a fixed rate, that problem goes away. The other one with respect to the chicken and egg problem that you discussed is this off-policy correction that tries to kind of think about, given a trajectory that you've seen from or given the goal that you commanded, what would be the the low-level policy that would be able to get to that goal. So there are a few things that you can do to address these challenges, but overall, this makes this problem quite challenging. I think you're totally right.
I see. Thank you.
Mm-hmm.